Hello grade 11s, this is Physical Science. My name is Gillian, and today we are going to strip away all the confusion around friction, and we are going to get to the nitty-gritty of it to help us to see it more clearly. So we are exposing friction today. So let's have a look at what causes friction. So on my board I have an overview. We have the cause of friction, and then we have the two kinds of friction. There's static and kinetic. So what causes friction? Well, when we have two surfaces that are rubbing together, then we have friction. The output of friction is heat, so things get hot. And you will know this if you've fallen on the grass and you've slid. It burns, you get a grass burn. Okay, so that's two surfaces, your knee, your skin, rubbing along the grass, they're interacting, they're rubbing together, there is friction, and there is a burn, it gets hot. So that is what friction is. It's a force of friction, and it causes an increase in temperature in those surfaces. There are two kinds. The one is static. And as it says, static is stationary, so that is the friction that will occur when something is not moving yet. And then we have kinetic friction, and that says exactly what it is. Kinetic is moving, like kinetic energy, it's moving energy. So when something is moving on a surface, there is friction that retards that movement. What about friction? Because friction is quite a tricky force. Well, we would think that it is dependent on how much of your knee is on that grass. In other words, the surface area comes in contact. But that would be incorrect thinking. In actual fact, friction is independent on the surface area that is in contact with the second surface. So here I've said area does not influence, it has no bearing on the size of the frictional force at all. What does have a bearing on the size of the frictional force is the mass of the object. And so the more mass an object has, the greater the gravitational force, and so then the frictional force is going to increase. So frictional force is definitely dependent on the mass of the object. The other thing that friction is dependent on is the type of surfaces. So if you think about smooth surfaces versus rough surfaces. So example, the tarmac is quite rough. So tires on tarmac, okay, so a tire is also quite a rough surface, that rubber is quite rough. That would affect the amount of friction or the size of friction between those two surfaces. If you've got a smooth surface, then those surfaces would then have less friction between them, but they still will have friction. So the type of surfaces will give us a frictional force of some size. So it's dependent, the size of the frictional force is dependent on the types of surfaces that are rubbing together. Okay, so let's have a look now in detail around this frictional force and what it, we can break it up into static and into kinetic friction. So a long time ago, before you were born, in 1985, there were restrictions around the amount of petrol that Formula One racers were allowed to use. And they restricted that. And all of a sudden, all these drivers were running out of petrol, and they got out of their vehicles, their Formula One cars, and they pushed them to the finish line. So I want to use that example today. So if you look on my screen, you will see this Formula One car that's sitting here. Now, this thing is just sitting there. There is no one pushing it. There is no applied force. And because there's no applied force, there is no friction. Have a look there. That's the first thing we need to bear in mind. No applied force, no friction. The static friction, this is stationary, so we're dealing with static friction. There is no static friction, it is equal to 0. There's no person pushing it, there's no applied force, it is 0. Static friction is 0. Now what happens, our driver gets out, I'm going to draw him in. Okay, so here's our driver, just excuse my drawing. Okay, there he is, okay. He obviously has to be over here because he's got to steer the car so it doesn't go off the track. And he starts to push. However, the car does not move. Now, if you go and watch these old videos, you'll see the driver gets out and he's starting to push and there's no movement. But because there is an applied force, here's the applied force, he's pushing against the wheels. Okay, the applied force, he's pushing against the car, he's pushing it to move it. There's an applied force. There is frictional force, and it is static frictional force. As he pushes, he's going to increase that applied force. Obviously, he's going to push harder and harder. And the amazing thing happens, as he pushes harder, the static frictional force matches that. And so as you increase the applied force, the static frictional force increases. And so this over here, static force matches the applied force. The car is still not moving. It gets harder and harder to push that car. And then all of a sudden, that car starts to move. At that point where the car just starts to move, the object is starting to move and the static force is just overcome by the applied force. So if the object then starts to move, just as it starts to move, that static frictional force is overcome and the static frictional force will be at its maximum. That's the maximum it can ever be. Interesting, isn't it? So let's have a look how we can put this into words. So we've got static friction. What is it? It is the force that is stopping movement. So friction always works in the opposite direction to movement. It opposes, have a look there, it opposes, it goes against the tendency to move. Why only the tendency? Because this object isn't moving, but it is intending to move. So the applied force is being applied, it is intending to move, and so it is the tendency of motion of a stationary object. It is something which is static. It is not moving yet. It has to be relative to the surface. So that is the definition for static friction. We write the maximum static friction. Remember, that's just as the car is starting to move or the object starting to move. We write it like this. It is a curly F with a little s. That S denotes, it tells you that it is static friction. The curly F tells you it's friction. And then there is the word max. So max means that is the maximum amount of static friction just as the car is starting to move. So how are we going to write this or draw this on a graph? So in science, we like drawing on a graph. We like to see the relationship. It is a picture of the relationship. And on the x-axis, I have applied force, because what we're doing is we are applying the force. The driver is pushing the car harder and harder and harder. So we can then measure the applied force. What is then happening to the dependent variable? And the dependent variable will be this force of friction that is placed on the y-axis, the dependent variable. Well, it increases and it matches. So as the applied force is increased, can you see that? Increased. So the frictional force is going to increase. And it increases, you can see this line, it is a straight line, and it increases to a point. So we'll come to that a little bit later. We'll finish up this graph. But you can see that this relationship is a proportional relationship. As the one increases, the other is going to increase. So here I have this section from the naught value to over here, to where we finally reach the maximum static friction. And this part is equal to the applied force. So as the applied force increases, so the static friction increases, and we get this relationship here. Right. Now this picture is of a driver that's actually driving it. So you can see the background. You can see it's moving fast, right? So you're going to just ignore that for now. We're going to pretend that our driver is now pushing this vehicle. Okay, he's pushing. There's my driver, he's pushing. And it is now moving. So he's pushed, it hasn't moved, and then all of a sudden the vehicle starts to move, the car starts to move, and that becomes easier. If you've ever tried this, if you've ever tried pushing something and it's really, really hard, and then all of a sudden it's almost as if something gives way and then it starts to move more freely. What happens is, as it starts to move, the static friction is overcome and another type of friction takes over, and that is the kinetic energy. Kinetic friction. So the kinetic friction is the friction that is opposing the movement, but it is less. It is much less than the static friction, and it is less than the applied force. Okay, so it's less than the applied force. Becomes much easier then to push that car. So if we look at our graph, what's happening here? Well, we see that we've reached the maximum. There we showed that in our last one. We've reached our maximum, and then all of a sudden that car is moving, and it's moving much more easily. So there is a drop in friction and the kinetic friction. So it drops, that's the drop down here, this purple line. And then look at it, look how much less it is. Okay, you can see the frictional force, it's much less than the maximum static frictional force. So the kinetic frictional force is much less. And look at it, it's a straight line. It is constant. Okay, so it is a constant value for the movement of that vehicle. Grade 11s, we are going to take a quick break, and then we're going to look at what affects this frictional force. If it's not the area, then what is it? Right, I'll see you after the break. Welcome back, grade 11s. We are exposing friction. So let's have a look now at what actually influences the frictional force. On my screen, you can see that we are dealing with both the types of friction, the static friction as well as the kinetic friction. Now, in both cases, friction opposes motion. It is very, very important that you learn this, because we're talking about it acts in the opposite direction of movement. Okay, so it is opposite to motion. When we answer questions, we need to ascertain what direction the object is moving in. So I have two pictures here on my screen. One is on a flat surface, this little one here, this box. Let's say it is moving in that direction. So that is movement or motion. What then is my frictional force? In which direction is my frictional force going to move? So is going to act. So if movement is in this direction, let's just say to the right, I'm just going to say to the right, the frictional force is going to be between the surfaces, so that's between the box and the surface that it's on, and it is going to be in the opposite direction to movement. Opposite direction to movement. Now, what about an object on a slope? So we need to be very careful when we are dealing with objects on a slope. If the object is moving up the slope. I'm going to change my pen so we can keep this constant. So if my object is moving up the slope, that's the movement going up the slope. How is friction going to work? Well, friction is going to work in the opposite direction to movement. And so friction is going to work here. It's going to work between the surface of the box and the surface of the slope. I've drawn these arrows quite big. If there's movement, obviously that arrow that's representing friction is going to be a little bit smaller because if there's an increase in velocity, then the movement has to be bigger than the force creating the movement has to be bigger than the retarding force of friction. What happens if this object is moving the other way around? So if it's moving in that direction, okay, so there's movement. If it's moving down the slope, there's still friction because the object is still on a surface. It's still on a slope. So friction is going to work in the opposite direction, and it's going to work up the slope. Our second thing that we need to really get to grips with, and that is that the frictional force, both static and kinetic, is directly proportional to what? Well, to this normal force. It's directly proportional to the normal force. We get our equations from this relationship. We're going to have a look at them in a moment. But let's look at how that's going to impact our drawings and what the forces are going to look like. So over here, I've got the first example, number 1, the box on the horizontal slope, the horizontal surface, there's no slope. The normal force is the one that acts up on the object. I'm going to change my color because that doesn't look like you can see it much. So this is the normal force, okay, force normal. Some of you write it with a big N. That is the surface or the earth acting on the object that is sitting on the surface or sitting on the earth. What is that equal to in magnitude? It's equal in magnitude to the gravitational force. Okay, and we know that as being ma, okay, from Newton's laws. So the force of gravity is equal to the mass times gravitational acceleration. So the mass of the object and the acceleration is 9.8 meters per second squared. We know that, right? So this is what the frictional force is related to. It is directly proportional to this normal force. So if we think about this, if we've got a light object, in other words, the mass is not big, then the force of gravity on it is going to be smaller than an object that is much heavier. It's got more mass. The normal force is going to be in the opposite direction, but it's going to have the same magnitude. If friction is about the interaction of the surfaces, and you've got an object which is being pulled down onto that surface with a greater force, obviously the frictional force is going to be bigger. So the greater the mass, the greater the frictional force. How is that related? It's related to the normal force, and the normal force is the same magnitude as the gravitational force, opposite in direction. What now about an object which is on a slope? So let's have a look at this. We have to think back to our forces and breaking them up into components. So we've got a force, whoops, that's a bit skew, of Fg. Okay, so that is our gravitational force. If we break this up into its components, we're going to have a force. Let's just say it is moving down the slope. Okay, so we're going to have a force like that, which we call F parallel. It is parallel to the surface. And we have a force like that, which we call F perpendicular. Why? Because it is perpendicular to the surface and the object there. So perpendicular to the surface. What is the normal force? The normal force is the surface acting upwards, like that, isn't it? So this would be the normal force, F normal, and it is related to the components of gravitational force, the perpendicular component. It is the opposite direction, but it is the same in magnitude. That means that we can, if we put something on a slope, so it's flat on the ground, we can reduce the normal force by putting it up on a slope, can't we? Because we have then changed the effect of the normal force by putting it on a slope. If we change the normal force, we can change friction because they are directly proportional to each other. Have a look there. So the only way we can change frictional force is by changing the normal force. How can we change the normal force? We can change the normal force by placing an object on a slope. And that is why it is easier using an inclined plane to move heavy objects than to push them on the ground. So, how do we come up then with a formula that we can use? We have, for static frictional force, we have the fact that it is directly proportional to the normal force. And so we have our maximum static frictional force. Now, we don't work with the other, as the static frictional force increases, like on the graph, we don't work with those. Those get a bit complicated. So we only work with the maximum static frictional force. It is going to be directly proportional to the normal force. Directly proportional to the normal force. If we change the forces acting on the body so that we can change the normal force, then the frictional force will be changed, and that applies for both static and for kinetic friction. So we can also say that the frictional force, kinetic frictional force, is directly proportional to the normal force. We come up then with equations because we can't use the relationship for calculations. So what we can do is we can change things around and we can pop in a coefficient. It is a constant, and you've come across constants before. And the constant for kinetic friction and the constant for static friction is this symbol here. So it's a mu. It is a Greek letter. It's like a fancy U. And if we want to distinguish between static friction and kinetic friction, we put a subscript of S or we put a subscript of K. So that means the static friction, and that means the kinetic friction. So it is called the coefficient. That's the word. It is mu S, and it is a ratio. And a ratio doesn't have units, right? And this is the ratio. It is for static friction. It is the maximum static friction that we deal with, divided by the normal force. That is the relationship, or that is now the equation, the ratio for this coefficient. So we can say mu S equals this ratio. We can rewrite this equation, and I'm going to do that in a different color so we can see it. And we can rewrite it as, let's write the static friction, maximum static friction, equals mu s, or the coefficient of static friction, times by the normal force. Okay, so there's that equation that we're going to use. For the coefficient of kinetic friction, it's the same thing. It's u. It's that Greek u or mu, and we put a little k to tell us that it is a kinetic friction we're dealing with. It is a ratio. Here's the ratio here, so I'm going to draw it in. So mu k, or the coefficient of kinetic friction, is kinetic friction divided by, it's the ratio of the normal force. How can we write that in an equation that we can use without fractions? We're going to say kinetic friction equals the coefficient of kinetic friction times by the normal force. We have got time to quickly look at this graph and see how we can add to it. So we've already seen that the static friction is equal to the applied force. What we haven't said was that this holds true. So the static friction is equal to this, or it is smaller than. So as the static friction increases with the applied force, it is less than the maximum static friction. Over here, at this point here, where we overcome the static friction just as the object is starting to move, that is the maximum static friction. And we can see that it is equal to, then, the formula. It is related to the normal force. Remember, it's directly proportional to the normal force. As the normal force increases, so the friction is going to increase, and so we have this coefficient of static friction. What then? Well, as the object then overcomes, or as the person overcomes the static friction, we then have a drop in friction, and it is now called kinetic friction. There's a drop there, you can see. It is constant. Kinetic friction is constant. And here we have our relationship. It is the same relationship. They are both directly proportional to the normal force, but we now have got a coefficient so that we can use this relationship to calculate things. And so kinetic friction is equal to the coefficient of kinetic friction times by the normal force. Whoa, that was a lot, grade 11s. In the next lesson, we're going to work through examples and see how we can apply our knowledge that we've gained today. I will see you next time.